I want to start by saying a big thank you to David and the whole LOC and the staff at Caltech and IPAC for organizing this meeting in what must have been extremely difficult circumstances. We all know how much work goes into a meeting, and I can't imagine doing this during this time of hardship that was caused by the California wildfires. And as David said, I hope that by all of us being here, we can provide some support to the local community that has been affected by the wildfires. So 8 years ago, I attended Nodai Star 1, and looking back, I can confidently say that that was probably one of the best conferences of my entire career, except for the coffee. And it will come up again, David, trust me. There's no way avoiding it. And the reason why it was my favorite conference is because it brought together my two favorite communities in astronomy. That's the exoplanet community and the stellar astrophysics community, and we came together because we wanted to, and not because we ran into each other at a Kepler Science Conference or a TESS Science Conference, because we want to be in the same room and we want to discuss topics with each other. So the SOC tasked me with reviewing how we determine fundamental stellar properties and the caveats that are involved with this. But I want to take at least a few minutes to motivate a little what brings us actually together at this conference. And I won't pretend that I know why all of us are here. We all have different reasons for being here, but I would bet that many of us are here because our picture of exoplanet science looks a little bit like this, which is that exoplanet science is extremely exciting. Oop, there it goes. And it builds, there's lots of exciting developments that build on top of each other. But in the end, it's all grounded and rooted on some more fundamental science, and that includes the stars, which are one of the building blocks on which exoplanet science rests. So to be a bit more quantitative, there's sort of three main building blocks, I think, that are important, one of which, of course, is Nodai star, Nodai planet, the fact that we measure properties of planets relative to the stars, and we do this using the transit method. We measure radii relative to the radius of the stars. We measure masses relative to the masses of the stars through the RV method and microlensing. And even for direct imaging, knowing the star is important because the age of the star, for example, determines the mass of the planet, depending on its luminosity. This is for young planets important. And even for mature planets, ages of stars are important to interpret possible biosignatures that we might detect in mature planets using future missions. So some of you may be here because you don't actually like stars at all, or perhaps you don't like the effects that stars have on your data. Of course, stars are noisy. If you want to detect exoplanets and you study them, you need to take into account noise. So I phrased this Nodai star, Nodai noise. We all know, of course, stars are noisy, and if you have observations of planets, that can get in the way. I'm showing some recent examples of this. There will be lots of sessions, lots of talks of this topic. But on the left here are JWST observations of 55 Cancri, a bright solar-type star, secondary eclipse observations of 55 Cancri E, showing some structured noise that looks to be consistent with stellar granulation or some other type of stellar variability that hasn't actually been confirmed, but the timescales at least look consistent. On the right is TRAPPIST-1, as observed by JWST, showing a clear flaring event. We'll hear about this from Ward Howard later this week. And of course, also radial velocity observations are affected by the star, and a recent example here is shown for a Barnard star showing espresso radial velocities that are heavily affected by the rotation of the star that needs to be removed in order to tease out the small signatures of planets. And then the third main pillar, and this is my favorite one, is that we can actually, of course, understand and learn something about planet formation by understanding the stars. So Nodai star, Nodai formation. This is rooted in the fact that fundamental properties of stars are linked to the formation processes of planets. That is true for ages, masses, metallicities, stellar multiplicity, all of which are things that we will hear about this week. I'm showing two seminal examples of this planet-star connection on this slide. On the left, the famous gas-giant planet correlation, the fact that gas-giant planets are more common around more metal-rich stars. And on the right, the seminal result from Kepler showing that small planets, sub-Neptune-sized planets, occur more frequently around cooler stars. So moving on to this, we're now actually at an era, and I think Jesse Christensen will be talking about this a bit tomorrow, where we can actually study exoplanets on a galactic scale. We've detected so many exoplanets around so many stars that these stars are actually in different populations of our galaxy, and we can start to study and discover exoplanets in a galactic population context. Of course, Roman will take this to a whole new level, but even with Kepler K2 and TESS, we now have exoplanets orbiting stars that basically represent certain stellar populations in our galaxy. And I want to, before I move on to the more mundane task of talking about stellar properties, just highlight one recent example, because I don't think it will be shown later on in the conference, that I think is really intriguing and goes towards this exoplanets in a galactic context. So these are two results from early career researchers. Casey Brinkman, who recently graduated from UH, and Ankarat Weeks, who I think is in the audience, who's at UCL and will soon graduate. On the left, Casey determined the core mass fraction of rocky, short-period exoplanets. So this is basically measuring their radii, their masses, knowing that they likely do not have hydrogen helium envelopes, and determining a core mass fraction, a composition of those planets that way. And this is compared to the equivalent, what we call the equivalent stellar core mass fraction, which is estimated from the atmospheric abundances of the star. And what Casey finds is that there is a very weak link between those two, if any at all. It's basically a scatter plot, and there's not a lot of correlation between the two. Now, on the other hand, what Ankarat found is that if you plot planets, the same planets, short-period rocky planets, in a mass-radius diagram, you do find a correlation with stellar age, namely that younger planets appear to be denser. The younger planets are the ones that have the darker colors. So there's no apparent correlation between abundances of stars and rocky planet compositions, but there is a dependence of rocky planet compositions with stellar age. And that's a bit counterintuitive, because galactic chemical evolution tells us that stars change as they age. They become more enriched in metals as type 1a supernovae go off in the galactic context. So this is interesting. It tells us either that perhaps the uncertainties in our abundances are too large to detect these subtle effects that imprint themselves in the ages and the compositions. Perhaps it's different elements that we need to look at. In Casey's work, we looked at magnesium and silicon abundances. Or perhaps there's a different reason altogether for the fact that rocky planet compositions seem to depend on the age of the star. Okay, so with this, I will now move on to my original task, which is to review how we determine fundamental properties of stars. And there are many ways of doing this, of course, and I will talk about what I call the classics, the classical methods. So that includes parallaxes, interferometry, broadband photometry, spectroscopy, and astroseismology. And I know it's crazy to call astroseismology a classic, but I think we're there now. It's been around for long enough. So I'll review these methods, but of course I want to also highlight that there are other methods, more what I call modern methods to characterize a star. Jamie Taher will give an invited talk later today who will touch on a few of these. That includes rotation periods, gyrochronology, the way that we can use rotation to age date stars. We can use other time domain variability phenomena such as granulation to determine surface gravities. We can use very precise transit light curves to derive densities of stars, and I think there will be several talks on this also later today, in fact, right after myself. And then we can also use kinematics, galactic kinematics of stars, to age date stars as an ensemble. And this is an example of an age a velocity relation from the past project led by Ji Wei, who's here and is presenting a poster on the results from the survey. So let's dive right into it. I'll call this the basics. Let's start with parallaxes and fluxes. How do we use those quantities to derive fundamental properties of stars? Of course, the way to do this has been revolutionized by Gaia. The fact that Gaia has provided us distances to better than 1% in most cases for basically all of the exoplanet host stars that we might care about. This will change in the era of Roman, but for now, this is still a true statement. And if you know the distance to the star, and you have another observable, the bolometric flux of the star is measured on Earth, you can directly calculate, just from the inverse square law, a fundamental property of a star, its luminosity, its total energy output. You can go a step further and use the fact that the effective temperature is defined for the Stefan-Boltzmann law to actually calculate the radius directly, but that requires you to know the temperature. I'll get back to the difficulties of doing so a little bit later today. But essentially, we can measure luminosities and radii for lots of stars very precisely because we have Gaia parallaxes. And this has, of course, been capitalized in the community. I'm showing one example here just to illustrate the impact that this has had on the Kepler exoplanet sample. So this is the Kepler exoplanet population showing the radius on the y-axis and the incident flux on the x-axis, the hot planets here on the left, so higher incident fluxes on the left, and cooler planets on the right. This is the distribution before Gaia, and that was Nodai Star 1, right, before the Gaia data release that we're currently using. And I will flick forwards and backwards now of how the radii of these planets changed by just revising the radius of the star. the only thing that we've been doing here. We're only revising the radius of the star. And I really like showing this. This is from Travis Berger's PhD work, because it really nicely shows how the planets snap into focus, and some demographic features also snap into focus, including, of course, the famous radius valley or radius gap between the sub-Neptune-sized and the super-Earth-sized planets. There is a bottleneck, however. We're not done. And the bottleneck now are no longer the distances, but how well we can actually measure bolometric fluxes. And so in a paper led by Jamie, we've looked into this a few years ago, where we've basically taken bolometric flux measurements from different methods, from different published values, and compared them to each other for the same stars, and plotted that as a function of temperature. So the y-axis here is the ratio of bolometric fluxes as a function of temperature for 3 different samples. And you can see that there are systematic differences as a function of temperature, and those systematics are sort of at the 1% to 2% level. So that might seem small, and it's pretty challenging to measure bolometric fluxes of stars to that level, but it is now the limiting factor in our ability to measure luminosities, right? Because the distances, even though it goes in a square, is known to better than 1%, and so the bolometric flux with a 2% systematic error is now the floor at which we can accurately measure luminosities of stars. This is not at all taking into account effects of binaries. We'll hear a lot about binaries and the connections in an astrophysical sense to planet formation. But binaries, of course, also cause biases in this by biasing the measurements of the bolometric flux. So accurate absolute flux measurements have become, I think, a bottleneck for capitalizing on these really precise distances that we have from Gaia for exoplanet host star characterization. The good news is that there are solutions in sight. In fact, we have spectrophotometry from Gaia itself, BPRP spectra, which is shown here in the bottom left. These are residuals, so some flux standards that still show residuals at the few % level. But we really should be using Gaia BPRP spectra with the caveats that exist for host star characterization. But there's also missions in the future, including the near future, SphereX. We'll hear about SphereX later this week, that will provide spectrophotometry in the near infrared. And the Landolt mission, which we'll hear about from Peter also later in the week, that will precisely or accurately pinpoint the absolute flux calibration for stars. Okay, so moving on to some other methods, which I call the truth, which is interferometry and binaries, which are usually we refer to as methods to determine fundamental properties of stars that don't have a lot of model dependence. And so they're as close to the truth for single stars, or for all stars, of course, for binaries, that we can get. So optical long baseline interferometry has long held a very important role in doing this. And the reason is because interferometry allows us to measure the angular size of the star, the angular diameter, which is shown here as the symbol theta. And with the angular diameter of the star, you can directly, in a model-independent way, combined with the distance, measure the radius of the star. But you can also, the only way to actually measure, as defined for the Stefan-Boltzmann law, the temperature through observables, is by combining the angular diameter of the star and the bolometric flux. Again, it's the consequence of the inverse flux law in the Stefan-Boltzmann law. So you can then use these measurements to create empirical HR diagrams. Casper is in the audience. Casper, together with Tabby, have done this. This is now 2017 in the last Nodai star, an empirical HR diagram, measured luminosities or radii and temperatures from interferometry. But we can go even further. We can actually resolve the surfaces of stars using interferometry. And you might think that we mostly do this for red supergiant stars, stars that are really large in the sky that we don't really find planets around. But we have now actually entered an era where we're doing this for nearby sun-like stars. So this is an image shared by Rachel, who will talk about this later today, of Tau Ceti, a nearby sun-like star around which we're trying to detect planets. And here's a surface map of spots, of temperature, of intensity, as resolved using the Chara array. And of course, these maps tell us something about the fundamental properties, but also about the activity of stars. But also interferometry has its caveats, and those caveats are that to do interferometry, you need to calibrate, calibrate, and calibrate. And calibration is important because the visibilities, which we measure from interferometry, pass through Earth's atmosphere, and so they're reduced, and so we need to observe calibrated stars. And again, in Jamie's paper a few years ago, we looked into this, and we found that there are actually there are differences at the random level, but also the systematic level of diameters measured from different teams as a function of the angular diameter of the star. So if the star is fairly large, the agreement is quite good, even though there's still some scatter. But then as the star becomes smaller, there are systematic differences between measured diameters. And that makes sense because as the star becomes smaller, the less it is resolved in our observations. If you don't resolve your star well, the calibration errors start to become important. So we deduced from this that there are currently sort of 4% systematics in the angular diameter scale. That translates, of course, into 4% systematic in the radius scale and a 2% systematic error in the effective temperature scale because of the relation between the temperature and the bolometric flux and the angular diameter. So we need more well-resolved interferometric angular diameters to really lower the floor on our fundamental temperature scale and our temperature calibrations. Now, luckily, there are efforts to do this. I'm showing here 2 examples, again, from students that are working on this. These are both examples using the Chara array, but of course, we also have other interferometers, including the VLTI at ESO. But this is work led by Ashley Elliott on the left, who's working with Tavi Boyajian at LSU, showing a measurement of the angular diameter for 51 areas. So this is the visibility, which is what we measure in interferometry as a function of spatial frequency. And those of you who are used to looking at these graphs, the lower you resolve down the star, the smaller the visibility, the more you're actually resolving the star, and the smaller your calibration errors will be. So these are very well-resolved observations. On the right is an example of by Arnab Johan, who's a PhD student working with Tim Betting and me at the University of Sydney. And in this case, we're actually resolving the star past the first null, and we're able to put some constraints on limb darkening. Now, binaries are important. I won't actually have time to talk about binaries much. I want to mention them. Of course, there are fundamental calibrators, both eclipsing binaries and astrometric binaries. But there are still limitations even for the binary star calibrators, and that is that most of them typically have solar metallicities. As we push towards these non-solar metallicity stars in the galaxy, it's important to have these calibrators at significantly non-solar metallicities, and also at different evolutionary stages. A lot of the eclipsing binaries, in particular, are main sequence stars. Again, we have a lot of prospects for improving this. Gaia will produce lots of binaries, including astrometric binaries and spectroscopic binaries that we can use for this. But I also want to point out TESS. TESS is discovering lots of eclipsing binaries that are really bright. So this is from Andrei Prisha's catalog showing the G-magnitude distribution of TESS eclipsing binaries, many of whom are very bright. So we can go out, get radial velocities, and fundamentally measure radii and masses for these systems. And there are lots of posters, so I was very happy to see this, lots of posters here at this conference that talk about this, the fundamental way of measuring stellar parameters using binary stars. Okay, I want to spend a few minutes on the classic, which is spectroscopy. Spectroscopy is, of course, a very fundamental method and very important method for understanding host stars. A few examples here of the impact this has had in the recent past. On the left is an example of measuring detailed abundances of stars in wide binaries and finding differences in the abundances of elements between the 2 binary pairs as a function of the element itself, and some evidence that these differences in the elements of the 2 stars that were born from the same cloud are due to the ingestion of planets. So this is the planet engulfment model that's shown here in blue that seems to be consistent with the data. On the right-hand side is an example of an idea that has been around for a bit longer, which are differences in abundances of solar twins relative to the sun as a function of condensation temperature that appears to be independent of galactic chemical evolution and may be tied to the formation of small planets. The point I want to make here is that this is a very powerful method, but the effects are subtle. Look at the scale here. This goes from -1.1 to 0.1 dex. So you really need to measure your abundances very precisely in order to tease out these effects. And the challenge is that oftentimes as you move away from solar twins or solar analogs, it becomes very difficult. So on the left, this is work by Natalie Hinkle from some time ago now, showing that if you have different teams measuring the iron abundance in stars, you get differences. The different letters of different teams that measured the iron abundances for 4 different stars, and you can see that the scatter can be up to about 0.1x, so much larger than the effects that we want to tease out. Another important point I want to make is that temperatures from spectroscopy can be measured very precisely, but they need to be tied to the fundamental temperature scale from interferometry and photometry. The right-hand side here shows this for the apogee survey, so this is the difference between the spectroscopic temperatures and the photometric fundamental temperature scale, which itself, of course, is calibrated on interferometry as a function of metallicity, and you can see that the differences can be up to a few hundred Kelvin. And so it's important to calibrate your temperatures to the fundamental scale. So I would state that uncertainties in the analysis of stellar spectra are still limiting our ability to really probe small effects in planet formation signatures. The exception here are perhaps solar twins. But the good news is that we have lots of data. We have lots of spectroscopic data from surveys such as Apogee, Galau, and Foremost that are really providing a lot of spectroscopic data that we can use to improve the situation. Okay, now finally, I'll come to astroseismology. And I won't spend a lot of time on the details because the person who taught me all about astroseismology will speak later in the section. So this is astroseismology, the way to peer inside of the stars. We observe brightness variations. We perform a power spectrum analysis. We get peaks. These frequencies are P modes, pressure waves that propagate through the star. The main takeaway is that the fundamental thing that we can measure from astroseismology are densities and ages, because we probe the sound speed and the sound speed profile within the star that changes as the star ages. So there have been many results between the astroseismology and the exoplanet community, one of which is, of course, the radius valley, which looks very clean if you use only astroseismic systems. This is a paper in prep by Mariam Saeed, who's a graduate student at Columbia University, who's about to publish a homogeneous catalog of astroseismic detections from Kepler. But of course, this has been pointed out and analyzed previously by Vincent Van Allen and also Eric Pedigura. So we see a very clean gap if you measure the radii of stars really precisely, and you also use densities to derive radius ratios really precisely. But we also learned something about architectures of exoplanet systems. This is one of my favorite systems, Kepler-56, the first misaligned multi-planet system. And a very recent development is that Joe Long, a Hubble Fellow at the IFA, has actually done a more careful analysis and has found that it's actually only the core of the star that's misaligned with the multi-planet systems in the system. And the outer envelope, in fact, appears to be aligned. So there's still some surprises that we get even after all these years of analyzing Kepler data, including the dynamics of exoplanet systems. But I want to wrap up by talking about one particular system, which is a new results that is led by Yaguang Li, a postdoctoral fellow at the IFA. The paper will come out later today, which is on HD 219134. Those of you in the audience will recognize perhaps the name. This is one of the brightest stars with transiting planets that we know of. There are two transiting super-Earths, one of which depicted here in this artist's impression. And so we went out to perform astroseismology of this star using KPF. We've obtained over 2,000 KPF RVs over 4 nights, which must be breaking some kind of record in the Keck archive. And we did this in order to perform astroseismology. So if you take a Fourier transform of all these RVs, you get a beautiful detection of oscillations down here in the bottom panel. So this is the power spectrum showing this comb of frequencies similar to the one that I've shown you before. This is really pushing the limits, because cool stars, this is a K-dwarf star. Cool stars have small amplitudes. Photometry from TESS is not suitable to do this, so you really need to use extreme precision or radial velocities to get there. So we have exquisite astroseismology, but there's more. We also have exquisite interferometry. So here's a visibility curve, again led by Ashley Elliott from LSU, showing the visibility curve of HD 219134, beautifully resolving the whole star almost all the way down to the null. So we have a fundamental measurement of the radius of the star, the diameter and the radius and the temperature, and we have fundamental measurements from astroseismology. The question is, do they agree? And the answer is, they kind of don't. And that's actually interesting. So here is the radius of the star as determined from interferometry. So if you just pay attention to this panel here, the radius from interferometry and the radius as derived from astroseismic modeling of the individual frequencies. And there's a difference of 4%, which doesn't sound like a lot, but if you have very precise measurement, that adds up. It's about 4 sigma. So it's very significant. So what's going on? Well, we've explored different ways. Of course, the inflation of radii of K and M dwarfs is something that's been around for a while, but this is an old star. It's about 10 gigayears old. So it doesn't have a strong magnetic field, and so the usual ways to explain radius inflation physically don't really apply. We looked into varying model physics, such as the mixing length parameter and the helium abundance, which also doesn't get us there. It doesn't really get us all the way to the interferometric radius. So keep in mind that this is a radius that comes from modeling the astroseismic frequencies. There are ways to get a model-independent radius, but this one is not model-independent. And so I think this is telling us something about model physics, the fact that we're still missing something in our interior model physics that is preventing us to get to this 1% level where we really want to be. Okay, just briefly saying that there is progress in this, of course, as well. This is an example from Chris Lindsay, a grad student at Yale, who's using astroseismology to constrain the convective core overshoot parameter in more massive stars. Okay, header has stood up, so I will, finish with this graph. I think the future for Nodai star and Nodai planet is very bright. And one of the reasons for this is that the stars that in the future will be most interested in, for example, for directly imaging exoplanets using the Habitable Worlds Observatory, are exactly the stars where we can use all the tools of stellar astrophysics to characterize them. This is an HR diagram of the so-called Tier 1 targets for the Habitable Worlds Observatory. And look at the color bar here on the, at the color bar here on the right. These are all very bright stars. These are almost naked eye FGK stars for which we can use all the tools that we have at our disposal to characterize them. And I think that signals a very bright future for this synergy going ahead. Okay, with that, I'll leave up my conclusions and take any questions. Thanks.
Okay, so we're just going to point out that we definitely want to encourage early career researchers to make sure they're putting their hand up and asking questions. And with that, I will take any questions for Dan, if there are any. And we do have 2 microphones, and so you do need to wait till you have the microphone so that the people on Zoom can hear.
Hey Dan, great talk. So JJ, UC Berkeley. So I had a question about your M-dwarf, where you're getting the little bit of radius discrepancy between interferometry and astroseismology. So is this a gray model of the M-dwarf? Like are the opacities gray? Are they frequency averaged? Or?
So we use, so it's a K-dwarf. It's not quite an M-dwarf, so but it is cooler than what we usually apply astroseismology for. Okay. So for the atmosphere, we use different prescriptions for the atmosphere. One of them is a gray atmosphere, but not all of them are the standard sort of gray atmosphere models. So actually, what you see here, the estimates are different teams that have estimated the age, or the radius, and the mass, in fact, using different prescriptions. So there are 5 different teams. This is fairly common to do, using different physical prescriptions, both from the interior, so for example, how you parameterize convection, but also different prescriptions for the atmosphere. And it doesn't seem to be that sensitive to resolve that discrepancy, at least not enough to really get to the interferometric radius.
Yeah, thanks.
Hi, Dan. This is David Charity, pretending to be one of the early career folks in the room.
You're excused.
So one thing that you didn't talk about actually was how well we understand the limb darkening. And I'm curious on your answers to that, especially because it's so important for the interferometric modeling.
Yeah, yes, very good. I think we'll hear from Jeff, in fact, about limb darkening derived from light curves and highly precise light curves. Limb darkening can, of course, also be measured using interferometry. You have to resolve the star past the first null to get those constraints. And the preliminary results, at least for the interferometry side, is that there are systematic differences between the limb darkening that we find from interferometry and the one that is being predicted by the model atmospheres. We haven't quite sort of wrapped our head around this yet in terms of actually publishing and interpreting it. But yes, it is important to test the limb darkening models. They're predicted from model atmospheres. I'm very curious to hear what Jeff will find from JWST, I think, from JWST light curve. Same thing, okay, so limb darkening is also in trouble, apparently. But yes, it's one of the things that we can investigate.
We have a question from online. Regarding the weak et al. Result, could it be an observational bias that low-density terrestrial planets produce small Doppler semi-amplitudes that can only be detected in older quiescent stars?
So we've looked into the observational biases regarding the mass measurements. We couldn't, I mean, Ankrat is here. I encourage you to read the paper. It's on the archive. There's a lot of tests that we've done to check whether there could be an observational bias in terms of course, measuring masses of small rocky planets is difficult. But we couldn't really come up with any that correlates with age in a way that produces the trend that we see. So again, I encourage you to read the paper. There's a lot of very thorough work in there addressing exactly that question.
All right, we have time for probably at least one more question. We'll go down here on the left. And if we can get our next speaker to come down and start getting ready, that might be useful.
Hi, Dan. Janice Lee, Space Telescope Science Institute. So what's the most important implication if the radius discrepancy were to persist?
What's the most important
Implication.
Well, the implication is that we shouldn't trust our models of the stars, at least for these K dwarfs.
Yeah, so one more level deeper. So
One
what
level deep.
in
Well,
yeah.
the fact that we can't, basically, if we can't reproduce something quite as fundamental as the radius, then we should probably also be careful with other parameters, such as the radius, the mass, the age, and the correlations between the stars and the planets that we deduce by correlating, for example, how frequent planets of certain sizes are with mass. So, at the few percent level, I wouldn't be necessarily worried about global trends that we see. For example, what I've shown before, that small planets are more common around lower mass stars. That will surely hold up. But as we probe the sort of more subtle effects, including the one that I've shown at the beginning, right, these rocky planet compositions where it's really small effects that drive, the effect of planet formation imprinting themselves on the stars, I think the few percent level in radius, however that propagates into things like age, becomes important. So, the high-level takeaway is that, use stellar models with caution, especially if you go to cool stars. But that's not necessarily news to the people that work with stellar models, of course. Yeah.
Okay, we will have to leave it there then. And if you have extra questions for Dan, ask him over coffee or via Slack. And we can go ahead and thank him one more time.